And we met in Zurich, where he did his postdoc in Denis Kortman group, and I think he's going to present some of the work he did in Zurich. And 2001,
talking about this low velocity range where there's a lot of interesting things going on even at the linear elastic limit, where we'll study wave propagation through structures. I'll go through that in detail through my talk. But what am I going to do with this particular, yes, sorry. So the Rayleigh speed, so typically your longitudinal wave speeds are 5 millimeters for 5,000 meters per second in a classical metal like steel or aluminum. Rayleigh speeds, we're talking about square root 2 times, or square root CS over square root 2. So we're far above that. Now, the idea here is to be able to, we're not probing impact velocities that are much beyond the wave speeds as yet, but eventually we will get there. So when you go to, so for example, our pressure shear plate impact is a single stage gas gun, which can reach a maximum impact velocity of 1,000 meters per second. But then you can actually have two stage gas guns, which can go up to 5-6 kilometers per second, but we're not getting there just yet. Any other questions? All right. So in a very short nutshell, the questions that my group and I we will be trying to answer over the next few years is basically in trying to understand solid-solid phase transformations in shape memory alloys, where you could use these for solid state energy, where a mechanical stress results in the phase transformation, and we're trying to understand the limit of the kinetics of these phase transformations at these extreme conditions. Okay, so that's the overall idea of what we're doing. So if anyone's interested in more details about this, we can always chat a lot more. Right, so let's come back to the problem that I'm going to be talking about today. So we'll be talking about linear elastic wave propagation through microarchitected silicon waveguides. So this was work that I started when I was a postdoc at ETH Zurich with Dennis Kochman, right there. I'm pretty sure a lot of you have known of him. Charlie was a postdoc with me. So he was a postdoc with Dennis, and we were working together. He was running the computational end of this problem, and we're especially proud of this particular piece of work because it was basically the computationalists and the experimentalists sitting together and pushing each other's boundaries all the time, right? And I'll show you how that process worked over time. So Charlie is now an assistant professor at the University of Washington in Seattle, and we continue to collaborate. Right, so the idea of why we need waves, I probably won't go into this in too much detail because some of this might well be obvious. One of the questions is, can you guide waves through pre-designed paths? Another direction that I've been very curious about for a while, not as an expert but as an observer, is in using this for cell sorting, right? The idea being, if you have a patch of piezoelectric material under a microfluidic cell, you use the vibration or the resonance of specific types of cells. So for example, it turns out that diseased cells have different masses and densities relative to healthy cells, and so people use this for cell sorting. And of course, there are these obvious applications in energy focusing, energy generation, and so on and so forth. We won't talk about the applications as much today because this was more of a fundamental study that we were entering, but it turns out that we're discovering how many more applications we can access with the capabilities we have. Okay, so I'm given to understand that I have a fairly wide audience, so I'll start with something that's textbook, and I'm sure this is kind of obvious for a lot of you, but for those who's not, the idea is to come up with an architected system. So here I'm showing you a one-dimensional spring mass system, and so you can simply use Newton's laws, and if you insert the traveling wave ansatz, what you end up with is a dispersion relation, right? And the dispersion relation is a relationship between the frequency and the wave number, or the inverse of wavelength, in your system. Now if I go to a two-dimensional system, right? So again, it's a spring mass system. You have a k vector, you have a wave vector which is in two-dimensional space. So what you have on the x-axis and the y-axis is the kx and ky components, and this is a two-dimensional periodic surface. And so we identify a Brillouin zone, which is to say that if I have information about the frequency wave number relationship in this fundamental zone, I have information about it everywhere in my system, right? And that's using the idea of periodicity. So now let's go one more complication, and my computational colleagues tell me that this actually is a serious complication because till here it turns out you can do things analytically, and once you go to beams, it becomes much more complicated to do so. So now let's take a beam unit cell, a beam-based architecture. So you have a gamma, which is the aspect ratio of your unit cell, which is dealing with rectangular unit cells. And the idea is we impose the periodicity of the unit cell, which gives me the so-called Bloch's theorem, which for those of you who work with waves is probably very, very fundamental. So I'm sure a lot of you understand this better than even I do. But the fundamental idea here is if I have information about the amplitude of displacement in my unit cell, I have information about the displacement field everywhere in my system, right? Which means now we've reduced the description of a wave propagating in a linear elastic wave here, propagating in a large infinite periodic medium to information in the unit cell. So how does this look like? I'll just talk about representation because we'll be looking at these representations to the talk. We basically define this Brillouin zone, and then there is a subset of this based on symmetry of your unit cell, which says that if I have information about everything going on in here, I have information about the wave propagating through my lattice. And so we call this the irreducible Brillouin zone, or the IBZ in reciprocal space, right? So this is the frequency wave number space. So the question we started off with is, there was already a grad student, and Claire knows Bastian, who was basically simulating waves in truss-based metamaterials. And so the idea is, it turns out that computations are very, very expensive if you want to fully resolve these things, or you could come up with a beam-based finite element scheme, where you basically define the finite elements based on beams. So what you end up with is a dispersion surface, which is now a three-dimensional surface, right? So you have kx, so this is a two-dimensional unit cell. You have kx and ky, which is the wave vector in plane, and you have frequency on the z-axis. Now what you see, this is from Bastian's computations, is you basically have multiple surfaces for the different modes of the wave propagating through the system. Okay. So how do we interpret this, or how do we represent this in traditional, for example, in traditional literature? Is one way of doing this is by taking sections through this dispersion surface, and what you see as the red line is basically the cross section of the dispersion surface, and we stack these in different ways. That's one way of visualizing these systems. The other way of doing this is by essentially taking a path along a cross section and mapping that out in the x-axis. We call this the k path, right? Just to give you an idea, we said this is the irreducible Brillouin zone, and we basically unwrap the intensity of the wave on these lines, and then use that to represent this plot, right? So now you can actually capture multiple modes in frequency space for a linear line, and this is assuming a given amount of symmetry, right? So if you have crystal structures that break, if you have unit cells that break symmetry, this begins to be a very reduced version of that three-dimensional surface. Okay, so we're relying on symmetry. So when I first went to ETH, one of the questions was, can we actually measure wave propagation through these truss architectures? And so we started off with this relatively simple but actually expensive setup, where we do water jet cutting of a 40 centimeter by 40 centimeter plate, right? It's an aluminum plate. We have unit cells that are about 5 millimeters in size, and this was the limit of the manufacturing process at some level. We glue a piezoelectric transducer right at this point in the sample, and then we excite the piezoelectric transducer. What you see here in that big blue box is a scanning laser Doppler vibrometry. It is essentially a fancy name for a Michelson's interferometer, which allows us to measure deflections at given points on my sample. Now this is a fairly expensive piece of equipment that we got at the time, and I'll tell you soon enough that for the specific problems we were interested in, this soon became useless. It is still useful for these scales, but it becomes very, very difficult to use them for specific conditions. Right. So what I'm showing you here is a square unit cell, right? Excitation is at the center. This is experimental data, and so what you see is excitation at the center, and you see the wave propagating out from there. Okay. So we went back to Bastian's computations, right? And we said, let's look at whether our experiment is able to capture the full dispersion, and for how many modes you can actually capture this dispersion. So what you see here, right, is the same picture that you saw before, but the background color intensity is from experimental data. So we take our position as a function of x, y, and or a displacement as a function of x, y, and time, and we basically do a three-dimensional Fourier transform of that data. And what you see here is one data set. And then if we go across these different cross sections, you can actually see that we are capturing these higher modes with very good precision. Of course, we can work on improving the signal to noise ratio, but we were still capturing the essential aspects of our data. And so I'm showing you 4 cross sections through this surface, right? So we were able to capture something up to, if I'm not wrong, the 3rd mode. We weren't able to go much higher than that because of the bandwidth limitations of our instrumentation at the time. So the data set was able to give us excellent information at this time. And so now if I show you the k-path data, which is exactly the same data as before, but just unwrapped along this line. The color map is the experimental data. The lines are from beam-based finite elements. So you're using, if I'm not wrong, Bastian was using Timoshenko beams. And the solid points are from fully resolved. So you resolve the beam as a bunch of 3-dimensional elements, and so these are fully resolved finite element calculations. And it turns out for the first 2 modes, the beam-based finite elements was doing a great job, and at some point it started becoming less accurate when you go into higher modes. So it turns out that yes, the experiments are useful, because then one of the questions would be, why do we even need the experiments if finite elements is doing a great job? One is 3D finite elements is expensive, and 2 is we expect that Timoshenko beam, we were expecting at least that the Timoshenko beams were doing a good job, but it turns out they do not do a good job when you go to much higher modes. Right, so what I'm showing you here is the square unit cells, and here I'm showing you data from the rectangular unit cells, and you can see of course that the dispersion relations are much more complicated here because of the because we broke one of the axes of symmetry. And if you go to much higher modes right here, you'll actually begin to see that there is deviation of the points of the lines from the experimental data, right? So it works with limitations. And this is when Charlie came along and said, okay, now can we create gradients of unit cells such that I can guide my wave along arbitrary paths either in real space in position or in frequency space, which means can I do frequency sorting of sorts. And Charlie basically came up with this idea of using rays. This is from, he borrowed this idea from seismology, where he basically said I can model this as rays, where if I assume local periodicity, right, this is purely in a computational sense, if I can assume local periodicity of my unit cell architecture, and if I know the dispersion of that locally periodic architecture, I can create gradients of this periodicity and model the propagation of rays using the time derivative of the position and time derivative of my k vector, right? And this is something that comes from seismology, and Charlie has done significant work in this direction in the last few years. But this also means that you need very smooth gradients if we actually want to realize these devices experimentally or even in actual device design. And this is where he came to me and said, yeah, sure, the aluminum plates work. He actually made a reasonably fancy aluminum plate, but we soon hit limitations on how much of gradients we can achieve because you have limitations in the manufacturing capability of these systems. So the fundamental requirement here is if we want to have smooth gradients, we want small unit cells or high density of unit cells within our sample. So if I was sticking with my water jet cut aluminum plates that I showed you before, I either have to make my plates really, really large, which makes it prohibitively expensive, or I need to improve the resolution of my manufacturing process. But when I do that, I basically move away from beams because I don't have slender beams anymore. So here is an example of one gradient we tried with the aluminum plate. This is a design, and you can see that there is a gradient of the unit cell architecture from a square to a rectangle up there, right? So this was over 20 centimeters, so it's a 40 centimeter plate. This is over 20 centimeters, and our unit cells are 5 millimeters, right? So if we want to play with arbitrary gradients, you will soon end up with steps, simply because we don't have infinite control on the size of the unit cell in these kind of plates. Yes? No, there's no matrix. It's basically beams and holes inside. Yes. So we needed to come up with higher resolution manufacturing techniques, and a lot of these 3D printing techniques we discovered were largely limited to polymers, where you have viscoelastic damping of the material. So we needed to decouple the material dissipation from the structural dispersion of the wave through the material, and that's when we started chancing upon different types of microfabrication techniques. And I happened to come across this idea in microfabrication of silicon, where it turns out chemistry and microelectronics have done great work in controlling how small you can fabricate structures. For example, in the microelectromechanical systems community, in the nanoelectromechanical systems community, they've worked a lot with chemistry in trying to figure out how best to fabricate small structures in silicon, right? So one of the major issues with this, or one of the major directions in the MEMS and NEMS communities, is you fabricate little devices on top of a 100 millimeter silicon wafer, right? So you fabricate little micro resonators that's sitting around a silicon wafer. So the silicon wafer was really a substrate for the incorporation of devices into it, right? So it was a device holder of sorts. So we went ahead and asked ourselves a question: can we actually convert a full silicon wafer into our wave guiding device by itself, right? Because the challenge with all of these applications that people have done is they only care about making very, very small devices. What we needed was a device itself that was large enough with a large density of unit cells, which are our individual elements of the device, right? So we ended up going this direction. And this was my first ever introduction to a clean room and microfabrication, so it was actually a great learning experience for me, because I discovered this whole world of microfabrication, which you can really use for experimental mechanics across the board. I think it's a widely untapped space for mechanics and experiments, right? So what we ended up is we asked ourselves a question: can I take a wafer and convert it to my waveguide, right? Sorry. So we start off with, so this is the final schematic of our fabrication protocol, which came after, I think, 8 months of trying and breaking wafers in the clean room. So what we have here is a silicon on insulator wafer. That's what we call an SOI wafer. The SOI wafer has something like a 500 micron to a few millimeters thick base layer, which is a single crystal of silicon. We have an intermediate 2 to 3 micron thick layer, which is a buried oxide layer. In microelectronics, they call this the box layer, simply because it's buried oxide. It's a silicon dioxide layer in there. And on the top, you have a very thin layer, which is about 10 micrometers of single crystalline silicon, right? Now, I could make my device out of this really big block of silicon, but then I'll also be limited in the number of unit cells I can fit in there, because I have a fundamental limitation on the aspect ratio of my unit cell. So what we ended up doing is you put photoresist, which is basically a photosensitive polymer, on the top and the bottom. We etch a window into the bottom surface, so you can use etching techniques to essentially etch a window into the bottom surface, and I'll tell you why we need this window very soon. And then we create our architecture on the top surface, right? And here we are limited by the resolution of the photolithography system, right? When I say photolithography, I'm referring to the ability to create a pattern on this photosensitive polymer layer. Now, in our case, the limitation was about 1 micrometer, because we use UV light to essentially expose specific regions of this photosensitive polymer. The UV light has a wavelength, thank you, a wavelength of about 350 nanometers. Now, technically, that would mean that you have a resolution of 3 to 600 nanometers, but then you have issues with the optics, and you have focusing, and you have diffraction limitation, and effectively we have a practical limitation of 1 micrometer in our etching process, in our photolithography process. Okay, so we end up etching the top surface, and it turns out that you can use hydrogen fluoride that basically gets rid of this intermediate box surface. So hydrogen fluoride, turns out, reacts not with the silicon, but with the silicon dioxide. And so what you end up with is a freestanding film with a 2 to 3 micron gap between a handle layer and the device layer, as we call it, where you can have whatever architecture you want in a freestanding surface. This is different from people in microelectronics where they would etch devices directly onto your wafer. And the problem or the challenge with these is you do not get complicated bending modes if you simply have patterns etched onto a large substrate. Okay. So what I'm showing you here in the background is our first device. I'll tell you what this yellow thing is in a second. So what you see as a slide curvature is basically because of a little bit of thermal warping of our device layer. These stars that you see is actually the window on the back surface, and the reason we're doing this is you'll see in a second. And what you're going to see here is you'll have unit cells that are 10 micrometer beams, 100 micrometer unit cell dimensions, and so we have something like 600,000 unit cells inside a 100 millimeter wafer or a 80 millimeter region of a 100 millimeter silicon wafer, right? So let's look at a micrograph of our samples. So what you're seeing here is the edge between the architectured region and simply the solid silicon. These are the windows at the bottom of the silicon, and if I zoom in, that's my beam, right? So I have about 10 micron beams and 100 micron unit cells, about over 600,000 unit cells, right? And the beautiful thing about these experiments is if you're careful enough, you actually end up with nearly 90 to 100% accuracy. You end up with very few broken beams as long as you're careful inside the clean room. So once we do this, like I said, it becomes extremely difficult or impossible to use the experimental technique we used before to actually excite waves or measure waves inside our system. So we had to go ahead and build our own experimental setup. So here I went ahead and said let's use a pump probe experimental technique where we use optics completely. So here we have a pulse laser source that comes in and excites the back of my film. That's exactly why we have the windows on the bottom surface. So we use a pulse laser, which is a 1 nanosecond infrared light source that excites the back of my film, and on the top surface we build our own interferometer. So the scanning laser Doppler vibrometer that I told you, the expensive big blue box, doesn't really work very well when you go to these very small scales. So we went ahead and said let's build our own, right? So the mechanism for excitation, the one thing I forgot to tell you is once we finish etching our silicon film, we actually deposit a very thin layer of aluminum on the back and the top surface. So we're talking about a 10 micron sample and about 30 to 40 nanometers of aluminum on the back of the sample, right? So you have the excitation that comes in, right? The pulse laser basically creates an optical to thermal expansion on your aluminum film, and that results in the excitation of a wave through your silicon wafer. I'm not going to go into details for the lack of time, but we can always discuss the details of the excitation soon enough. But what you get is an excitation amplitude of something like 1 to 20 nanometers, depending on the amplitude of, depending on the intensity of the source you're sending in. Okay. And then the idea with the interferometer is to use a Michelson's configuration, right? So we have a reference mirror. This is your classical, what we call a homodyne interferometer, where you have a reference mirror, you have a coherent light source that comes in, right? We then basically split the beam into two. One goes to the reference mirror, another one goes to your sample, and the interference between the two will essentially give you a change in the phase of your interfered beams, and that is a direct measure of your displacement. Now the catch with a homodyne interferometer is unless you stabilize two laser beams, right, these are terahertz beams, right, unless you lock them to a particular phase, it's very difficult to get spatial or displacement resolutions less than half the wavelength of the light source we use, which is about 300 nanometers for us. 300 nanometers resolution is not acceptable for our experiment because the excitation is on the order of 1 to 10 nanometers. So what we ended up doing was we ended up building a heterodyne interferometer, which, yeah, in principle with a homodyne system you can actually achieve picometer resolutions, but it involves a feedback loop which is a little complicated. We're actually moving towards that direction right now. But then we ended up building a heterodyne interferometer where one of your reference legs is now offset by a given frequency. So you use an acousto-optic modulator, which I haven't shown you here, I'll show you a second, that creates an ambient beat frequency. In our case this was 80 megahertz under an ambient condition when there is no wave propagating through the system. And when there is a wave that comes through the system, you actually measure the change in phase of this carrier frequency. So now we are not limited to the hundreds of terahertz frequencies of the optical wave itself, but more what's created by this modulation, right? Now this way, once we can track the change in wavelength or the change in phase, oh sorry, the change in frequency or the change in phase, that's directly related to the displacement in our system. So here is a schematic of the original setup. So we have a sample stage, right? So this is an XY stage because we needed to do automated scanning. We have a pulsed laser source that comes in, and that's exciting the wave at a given point on our sample, right? And on this side we have a continuous wave probe laser, which is the interferometer for measurement. We basically send this through a delay line, and this delay line is basically to match the optical path lengths between your reference and your signal beam. You send this through an acousto-optic modulator, which is essentially a piezoelectric element, and this basically results in diffracted beams. The diffracted beam has a frequency offset of 80 megahertz from my original electromagnetic wave. And so when I recombine these two beams that come back from the sample at the photodetector, under ambient conditions I get an 80 megahertz beat. Once I have the wave that propagates, this 80 megahertz beat is distorted, and I use that to measure the displacement of my point. So now I do, for a single measurement of a wave on this film, I would do something like 100 pumps at the exact same point on my sample, and I would scan my my sample so that I make measurements at multiple points. And I put all of these together and I build my full wave profile. So just to give you an idea of the experiment here, this is just one cross section. So what you see here is a microscope objective. The pump beam, which is the pulse laser source, goes in, excites the back surface of my wafer. The wafer is simply mounted on XY stages with a 3D printed holder. That microscope objective goes to the other side, which is where I have my entire interferometer to make measurements of the wave in my system. So I'm not going to go into details here, but we have a full semi-automated Python code that essentially controls the entire experiment. So we generate a pump laser pulse, which triggers the laser source onto your excitation point. We make a measurement of the particle velocity as a function of time at a given spatial position. We then indicate to the scanning stages to move by a given amount, to move my entire stage by 10 microns, for example, and then I make a new measurement, and I can do this in a semi-automated fashion for about a full day, and that would give me something like 100,000 points. Yeah, so this eventually is moving towards a fully automated system. So just to give you an idea of the amount of data and the amount of time it takes for one full measurement, in this case we were restricted to line scans. So we were doing line scan measurements on one particular direction. So we had about 100 points. To increase our signal to noise ratio, we average about 50 measurements for every excitation point, and this takes about 1 hour. So I said if we do a full day, we'll probably get something like 100,000 points, just to give you a rough idea. And that's a lot of data. So we will soon hit limits of how we save and analyze this data rather than actually getting a large data set, but we're not at that stage just yet. So our first measurement was on the square unit cell, because we needed to check if our fabrication technique works and if we can actually pick up the dispersion that we got from our large scale system. So we did an excitation at this point. We did a line scan. Like I said, the unit cell dimension is 100 micrometers. So we did 4 points per unit cell. So we have a resolution of about 25 micrometers, and so we basically scanned about 20 unit cells in this experiment. And that's really a very, very small region of our entire sample. This is experimental data from the excitation point itself. So we excite at the bottom and we measure at the top, and you have essentially a rise time of say 1 microsecond, which is much larger than the 1 nanosecond pulse duration of the laser pulse. We can discuss why if anyone's interested. And what you see is the excitation amplitude. We're talking about something like 10 nanometers in this experiment. explained all of this, and here we're talking about frequencies on the order of 10 megahertz. Now the one thing to remember is the modes that we capture, right? As I make my unit cell smaller, my first mode actually goes to much higher frequencies, so I will be limited in the number of modes I can pick up this experiment. So what I'm going to show you now is essentially a movie of the evolution of my displacement from my excitation point along this entire line. Okay. So you can very clearly see signs of dispersion. We can also replot this in a different way in a position time plot, right? So that's my excitation point, and the intensity is represented by the color maps, and I've mirrored this along the position space simply because I know it is a symmetric system, right? From here we can go ahead and compute our frequency wave number plot, right? This is from experimental data, and if I overlap this with the finite elements, which I'm not sure you can see very well, but you can see these blue lines, which is from finite element calculations, we see a near perfect match, with the exception that we're seeing this, the green lines are from out of plane modes, right? We shouldn't be seeing these intensities corresponding to these green lines in our experiment because we were making a measurement only along one line. So we should only be sensitive to one direction of the k vector. We were seeing some of these other modes which we believe is scattering from defects around our excitation point. Again, this is another detail that we can discuss further. So the experiments work, which means that for a periodic unit cell, which is a square unit cell, we're actually able to pick up the dispersion relations from both scales of our experiments. But that's really not the point of this. I mean, there's no point in doing that because we know that we get this information from our large plates, which at the end of the day is much simpler to do, right? The question we want to ask ourselves is, can we actually guide waves through arbitrary gradients? Can we create arbitrary gradients and guide waves through arbitrary gradients in our unit cell? So Charlie started playing around with his ray theory where he could do inverse design. So he could create a gradient of a design variable and use an objective function for the path of the wave to design the gradient of his unit cell architecture. So he said, can we actually try this in your experiment? So to start with, we decided to stick with only one design parameter. In principle, we can expand this to multiple design parameters of our unit cell, but simply to make things easier, we stuck to one design parameter, and we decided to go with this unit cell. For this, we need the spatial distribution of the unit cell and its dispersion relations, right? Because remember, we need locally periodic dispersion, and we need the gradient of these design parameters. The cost function is basically the path we wanted the waves to take, and in this case we chose this particular unit cell, like I said. All right, so what we end up with, this is a computational design. We said we want to guide waves in a figure 8 pattern for no obvious reason, simply because we wanted to play with it, right? The tools were ready, the experimental tools had been built, the computational tools had been built. We said, let's go play with it. So Charlie's optimization scheme, which I believe is tricky to play with, so I'll let him talk about it when you have the chance, resulted in a design gradient of that theta parameter that you saw before, which looks like this, right? And the question now was, can we go and build this in the clean room? To basically give you a zoom in inversion, this is basically a unit cell, and that's the figure 8 design that we wanted to look at. So we went back to the clean room, we said, can we make these designs? So what you're seeing here, what you're seeing here is one of those devices, and you can see the pattern that you saw in the computational design. Since we did not need the entire wafer for these experiments, we decided to make multiple devices on a single wafer, simply to save material. And here is the cross-sectional micrograph of a single device that we designed. So let's look at what this looks like. You can see at the window, you can see these star patterns that we were able to microfabricate beautifully. In this case, we actually reduced our beam widths by half. So we have 5 micron beam widths and unit cell dimensions of 100 micrometers. If I zoom into specific regions of the unit cell, of specific unit cells, you can actually see that we capture the gradient beautifully. And in these samples, we had nearly 100%. I mean, I don't have the quantification of the perfection of the unit cells, but we had nearly 100% perfect beams. Maybe one of our devices failed, but we made something like 5 devices, and pretty much all of our beams were perfect. So this is a very robust technique. And to give you a sense of the scales, the times involved in building these, of course, it requires you to have a clean room, but with that, this took 2 days of my time, whereas if we were to make a big aluminum plate, it would probably take 2 months in a machine shop, depending on the time they have and things like that. Okay, so while this does seem fancy and it does seem expensive, it's actually not too expensive as long as you have access to a facility that can do this. That's the tricky part here. So we managed to make the device. Does the device do what ray theory predicts? Because ray theory again is a simplification, right? So at this point we were restricted. This is the computational design of what this experimental design should do. Since we were restricted to line scans at this point, we decided to take 3 lines. We decided to take a first line here, a second line here, and a third line here to see if we actually guided the wave in a figure 8 in our experiment. Excitation is always at the center of this point, right? So here I have excitation, and you can very clearly see that the wave propagates, and here we did not do mirroring because you don't have any guarantee of symmetry. So this is actually experimental data collected throughout these positions and these times. And you can see the wave excitation is happening right here. In this case, we excited the wave to much lower intensities. We had our excitation at much lower intensities because we wanted to restrict killing the beams around the sample. So you can see that your amplitudes are restricted to about 1 to 5 nanometers. The interferometer picks up the data beautifully, so you have propagation, and you start seeing that the wave amplitude starts decreasing significantly around when your figure 8 ends, right? Now the other thing you're seeing here is reflection that comes in. So we seem to have some sort of back reflection that comes in. This was not predicted by ray theory, but it turns out that this is a function of frequencies that are much higher than what ray theory designed. So the ray theory, the computational design basically said that at 750 kilohertz, right, I should have a figure 8. But it turns out when we did further frequency analysis, this reflection is happening significantly at about 1 megahertz, if I'm not wrong, right? So there is a frequency dependent response that we were discovering in the experiment that ray theory was not really looking for, and it turns out that when we ran the FEM calculations for exactly those frequencies, we had perfect match, or nearly perfect matches. So let's go to the second line scan. So you have the wave that's still excited here. The wave propagates to this point, and that's when you see it pop up. And then you see the wave only come up at this region here, right? These 2 lines that you see here were noise because remember we're doing line scan. So at every position we're making a measurement, and at certain positions, because we were doing an automated scan, we had a little bit of noise. But we're able to see that the wave was unidirectional. It did not pop up in the second region, which would be the case if we had a symmetric design. And now you can barely see that the wave only propagates in one direction on the third line, but does not in the opposite direction, the negative y direction. Okay, so this is first evidence that we were actually able to guide a wave through an arbitrary gradient, which we really could not have done with, for example, the large aluminum plates. So at this point, I think I'm going to slowly start concluding the direction. So we are now moving towards the next phase where we're basically improving automation of the experiment, so we can do completely automated area scans. But in summary, what we did was we said, okay, current computational techniques were limited. Charlie came up with a much more scalable computational technique to be able to generate very large densities of unit cells, but the experimental techniques couldn't get there. So then we went to microfabrication, and we figured out we could actually make those waveguides. Now once you could make these waveguides in single crystalline silicon, which is as linear elastic as we would be able to get with practical applications, we had to go ahead and build our own system to be able to do pump probe experiments to measure the waves through these systems. At that point, basically Charlie came back to me, and this is the little game that Charlie and I used to play all the time over coffee, where I would say, okay, now the pump probe is working, what can we guide? Charlie came back and said, okay, I have a little trick with my automation scheme, or my optimization scheme, and I've now come up with an inverse design. And it turns out everything worked out quite beautifully. after 2 years. Like this was about 2 to 2.5 years of struggling with the experiments and the calculations. Like I said, we're now moving towards new limits. We're trying to understand, it turns out that the design space that we can probe and the type of phenomena that we can probe has blown up with these scalable techniques that we were able to study. So now we're trying to understand how much of scale separation can we achieve. Can we actually create 1,000,000 unit cells inside a 100 millimeter wafer, right? It turns out that people actually make 200 millimeter wafers for microelectronics. We started asking the question, can we actually make 1,000,000,000 unit cells on a 200 millimeter wafer? At which point the clean room engineer said, look, we're not getting there just yet, but maybe at some point we can think about it. The next thing we're trying to understand, the thing we're trying to do right now is, remember I said we were limited to line scans. This is primarily because we're using free space lasers, right? So then we had to carefully align the optics such that you could do line scans. What we're doing now is we're coupling our pump excitation to a fiber optic probe. So when we do that, your fiber optic probe is integrated into your scanning stage, and then we can start doing arbitrary area scans. So now you can actually pick up the position, the displacement field as a function of position and time throughout a two-dimensional area, just like we were doing in the aluminum experiments. And there's a very interesting fundamental question that we've just started looking at, and we're actually looking for ideas here, is in understanding what an interface means for an architected system. The question we're trying to ask here is, if I have a gradient like we had here, you have essentially the redirection of waves, but what's really the mechanism that's causing the redirection of waves at that region? It's clearly some sort of interface, but what is a sharp interface versus a gradient in an architecture system is something that we're trying to understand with the experimental system and from a theoretical perspective. We don't really know how to get to the theoretical perspective. We're trying to figure out a theoretical way of defining an interface in an architected system, but this is something that hopefully at some point in the future, Charlie, Dennis, or myself will come back to you about. And of course, we're trying to extend this idea to random microstructures. If I have a phase transforming microstructure, right, where I can shape memory alloys, can I use this idea of interface engineering and microstructure engineering to guide waves inside so-called, well, not metamaterials per se, but real materials with phase transforming architectures, with heterogeneous architectures, let's say, or a heterogeneous microstructure. Of course, we have the tools right now, and we can dream up of infinite problems to look at with these kind of tools. So if anyone has ideas or would like to discuss further, please do let us know, right? Thank you very much for your attention. I've basically posted the QR code for 2 papers that were recently published on this work. So if you need the papers, feel free to reach out to me, or you can just get information from here. But thank you very much for your interest and attention, and I'm happy to take questions if there are any.
Thank you, Vignesh. Are there questions in the audience?
Yes.
Antian?
Thank you for the nice talk. I was wondering, so here you want to guide waves using gradients of like a gradient of a material. Say, what's the advantage compared to guiding waves through, topological materials? People have been doing that a lot in wave physics, like you put 2 materials with topology and then the wave can be guided that way.
Can you define topology for me? I see that I'm not quite sure how I would think of topology.
I think an easy way sort of to do it is, say you have a honeycomb lattice, and if you change the size of the lattice, at some point the band structure inverts. You have 2 bands like this, and then they go the other way. So you put 2 honeycombs like that. And then when you send a wave, it can only propagate through the interface of the 2.
Yeah, I mean, the tools basically do that, right? The tools are basically allowing us to change the architecture. So we're not actually controlling the gradient of the material property. We're actually changing the gradient of the architecture of the material. So we actually can do that. Now, this was mostly about development of the techniques that we could do it. But of course, once we have it, we can clearly do, we can actually come up with multiple designs for topological waveguides. So I believe this is just another way towards that direction in a sense. Yeah. Because the gradient of the material property is a totally different beast altogether. I'm not even sure how I would get there.
There was a question. I have one. What is the cheapest if I want to test an idea? Is it to run a finite element or to build the experiment?
That's actually a question we're asking ourselves right now. We're looking at where we're basically trying to develop this trade-off between the finite element and the experiment, right? So if you have slender beams, finite elements are the way to go, right? Now if you want to do 3D FEM when you have stubby beams, it is my understanding that finite elements would still work, and I think finite elements is still the way to go there. But now the question becomes, if I want to extract, because for example the input to these optimization schemes requires local dispersion relations, and the moment we start going to more than one parameter of the unit cell, we are worried that the computations might begin to blow up. And the nice thing about the experiment, at least my expectation right now, is the cost of running the experiment does not exponentially increase with the increase in unit cells, right? For example, in a single silicon wafer, I can fabricate 100,000 unit cells with exactly the same time it takes for me to make arbitrary gradients with multiple parameters as a single unit cell with a square lattice, right? So the time it takes to make two different designs is actually not different at all. But this is not true with the FEM, because then if you want to extract local dispersion, it becomes more and more expensive. So we are looking for that divergence point right now. As of now, we haven't reached that divergence point yet, but we're looking for it right now.
Okay, thanks. There.
Thank you for the fantastic talk. It was super interesting. And just out of curiosity, on your last result, so I think it was 39, perhaps. Yeah, sorry, that should be
The one?
So it should be the next. Yes, so you see the wave that's coming, that's going to the right, then diverge to the top, but you don't see the wave that going around to the top, then right, then down.
So yeah, I see what you're saying. You're basically seeing this, but we're not seeing this intersection.
This is the other way around. I don't know.
Yeah. So it's actually a good question. We've been asking ourselves the same question. One suspicion is, no, one thing we know is that the wave speed the wave speed is anisotropic. So the wave speed in this direction is different from the wave speed in this direction. So it's possible we weren't collecting enough data at long enough times to see the arrival of that second wave, because that might have been slower. So that's the only hypothesis we have right now, but we're still trying to figure it out. The next thing to remember is, you see that the intensity of the wave is very, very weak compared to the other to the previous line scans. And so we've really not looked at the intensity of the waves propagating through, because now we are at a point where the experiments are still being done in air, in atmosphere, and you have a 2 micron layer between the device and the base layer. So now we're questioning ourselves if we need to do the experiment in vacuum, because you might have air damping and things like that. So the intensity is something that we're still figuring out, and this could be a direction where the intensity of the other wave was too weak for us to pick it up. In principle, it's linear elastic, so it should not matter much, but in the experiment we might have dissipation coming from elsewhere.
Another question from Rémi or somebody else?
Okay. And perhaps I missed it. It's a very nice question, but above the holes, the black stars, the rods are standing by themselves, but above the gray area, are they linked to the?
No, they're not linked. They're completely freestanding. The holes are basically to do the excitation of the beam, but you have a 2 to 3 micron region throughout the entire surface, which is freestanding. So we know that they're not in contact with the base layer.
Because yeah, it's but there is no flexion in their own weight, because the sample is very, very large compared to the.
This is true. Now in these devices, we actually did not make the device, like I said, over the entire. Oops, sorry. We did not make the device over the entire wafer, right? Yeah. And it's really a very light, because again, you're talking about 10 micrometers beams, and because we have slender beams, your area fraction or volume fraction of material is very, very low. So it's actually a very, very thin foil of sorts. The one thing that can happen, which you saw before, is when we do the etching, there is temperature buildup, which means the base layer, which is the solid layer, could warp under temperature. So it could have a heterogeneous temperature distribution, and then you could have some warping, which in principle, which basically warps the film on top. With these specimens, we did not have that problem. With our large specimens, we did have a little bit of curvature in our top film, but then we were able to verify because we have a microscope that essentially observes the film and observes the base layer. So we can verify that there is a gap between the two. Now the topology of the slow curvature of a large film, that's something that we can control by simply controlling the time that we do etching through, because then you have to control the temperature.
Thanks, sir.
Thank you.
If there are, Sébastien, one last question.
I don't understand why your black cross couldn't be much bigger. You couldn't remove everything, almost everything.
It's so one of the reasons is to give you a sense of the time scales, right? So you have ions that are bombarding your surface. Now a 10 micron film, it takes about 20 minutes to etch. A 500 micron film, so for example those crosses, it took us about 1 to 1.5 hours to etch. And there's always a competition because you have photoresist polymer, right? And then you have the gap, you have the exposed region of the photoresist polymer that's being exposed. The polymer is also heating up, and so there's always a competition between how much of material you remove and how much of the polymer you're burning away. So it's nearly impossible using these techniques to remove the entire base layer. And so even these crosses was something that the engineer in the lab and I had to sit and debate about and be like, give us a little larger of a region. So this is a problem. Yeah.
Okay. Okay, let's thank Vignesh again. And if you have questions, Vignesh will be around this afternoon.
Thank you.